that's 6, and 8 is negative 20, and 10 is negative 36. Okay, why have I drawn, so this is all, I've just converted the information in the table into a picture, and in fact 2 pictures, because now, what am I supposed to be doing again? Find the upper and lower estimates of this function. Okay, and all I know is that this function is decreasing. So I'm going to, I don't want to confuse anyone, but what I'm now going to do is I'm going to draw kind of a fake sort of, I don't know, kind of decreasing function. But this green I drew very lightly is pure speculation. I don't know the function independent of these particular discrete selected numbers. Okay, so what we're essentially being asked to find is an underestimate and an overestimate. Well, to find an underestimate, I'm going to use, min-ram or whatever. And to find an overestimate, I will use max-ram. These are not standard terms at all. But what I want to do is to apply a rectangular approximation method to find approximately what this integral is. But I want to underestimate the true value. Well, if this function is decreasing, then what I could, all I can say for sure is that this function is guaranteed to be less on the interval 0, 2 than it is at the end of the interval. Which is just a fancy way of saying, draw the smallest possible rectangle which matches the function. Since this function is decreasing, I'm going to use, you're back? I'm going to use a right rectangular approximation method on this interval. Okay, and now I just do the same thing again, right? Cha. This is an underestimate, and now because this function is negative, they are making you think a little bit. So now the minimum value. Oh my god. The minimum value that this function might have is actually at negative 4, and okay, I just keep doing this. The principle at work here is that for decreasing functions, RAM underestimates the true value. And so what we get is this. Alright, now, hold on, Data. I need a red. Can I have this red for a minute?
Okay.
Thank you. So anyway, now I just do it. What's this integral from 0 to 2? Is 24 times 2. It's okay. It's 48. This is 2 times 12 is 24. This is negative 4 times 2 is negative 8. This is negative 20 times 2 is negative 40. And this is negative 36 times 2 is negative 72. If I add those numbers all up, man, I don't feel like doing this. I think I get negative 46. Is that right? 46 and 20. No, that's wrong. Negative 48. Negative 48. Could that be right? 60, 72. Yeah. Negative 48. In other words, if this function could be as low, this interval could be as low as negative 48. Alright, going a little faster now through this. I think someone got bored and went away. Alright, very professional videos. If we then try to do the same thing here, I'm going to get that now if I'm following the max rule, I should assume that my function is as big as possible. And if I know it's decreasing, I'm going to use LRAM. So we get something that looks kind of like this. Yeah. It's a little bit counterintuitive. Well, okay. Yeah, this on the interval 4, 6, for example, I have to pause for a second to know what... No, that's just wrong. Sorry. If the function is, there we go. If the function is starts at 12 and ends at negative 4, then it possibly could be 12 actually for the entire interval, except for this sort of very last second. So we have to allow for that. And here as well, this function could be it starts at -4 and ends at -20. So if we're trying to overestimate, we should assume it's at -4 for the entire interval. It's actually easier if you sort of don't think about it too much, but the mixture of positive and negative numbers is sort of forcing you to really think what's going on for this last subinterval. It starts at -20 and ends at -36, so if we want an overestimate, we should assume it's -20 the entire time. Okay, and so now having applied LRAM consistently because this function is decreasing to get an overestimate, I now see that this function could be 64 and then 48 and then 24 and then -8 and then -40. So here we get 92, 88. I'm somehow suspecting that I made some kind of arithmetic error, but I bet not. But just let me waste one more second and check, because I would like to be right. 5 3 is 45. Yeah, this is right. Okay, what that means is that from all of this data alone, all I can say for sure is that the integral from 0 to 10 of f must lie somewhere between, and I mean this range is sort of comical, -48 and 88. And that sort of reveals how little I know when I only sample the velocity sort of every 2 seconds like that. But okay, I think this is a good example of the principle that that whether the function is increasing or decreasing determines whether LRAM and RRAM are underestimates or overestimates, and the principle of sort of max RAM and min RAM. Okay, good. And sort of drawing rectangles and thinking, and also reasoning with functions which are negative. Okay, really want to be done with this homework now. Time is it? Oh yeah. Okay. Good. Okay. Last two little problems, hopefully. 47 says, oh, not a little problem. 47 says, okay, I am now going to present to you this sort of obscure function constructed in such a way that it is composed of geometric objects that you know how to find the area of. And so here we have this point, -4, -1, and a line, and then we have a circle of radius 2, upside down, semicircle I suppose, and then this point, let's see, I think I've made a mistake. Oh, oops, I just totally wasn't paying attention to what I was doing. Ah, very frustrating, sorry about that. It's like this, it's a line, yeah, and then it is a circle of radius 2, but it goes there, and then up to here, cha-cha and cha-cha. So that's 4 and that's 6. It's the point 4, 2. Okay, so I've just reproduced the picture in the textbook, and now I'm just going to answer all these questions, man. This function is f. And so I just want to know what's the integral from 0 to 2 of f. What's the integral from 2 to 6 of f? What's the integral from -4 to 2? So I think this is like pretty easy. And the last, well, okay, I'll just kind of go as we go. What is this going to be? Well, the integral from 0 to 2 is just asking you for well, the integral from 0 to 2. So it's just this area. But of course, keeping in mind the fact that the integral is really sort of like the signed area under the curve, or the area under the curve. It's just the area under the curve if the function is positive, but if it's negative, you count that negatively. So what is the area of a quarter circle of radius 2? Well, if the area of a circle is pi r squared, then a circle of radius 2 will have area 4 pi, and a quarter of that will be pi. So the answer to this is just negative pi. Good. This makes sense because if you think of this as a velocity versus time curve, then when the function is negative, then the velocity is negative, and so the object is moving to the left. And if the object is moving to the left, this negative answer to this integral is correctly answering the question, what is the displacement on the interval 0, 2? If I was moving at a negative velocity for 2 seconds, starting at time 0 and ending at time 2, then where am I? Well, I'm negative pi to the left of where I started. That's the whole reason why we've defined integrals such that they have negative values when the function we're integrating is negative. Okay, what's the integral from 2 to 6? It's just the area of this triangle. This is 1/2, 4, 2, so that's just 4. What's the integral from negative 4 to 2? Well, I get this negative triangle of area 1, sure, and so this is just going to be negative 1 minus 2 pi, because that triangle has area negative 1, and this semicircle has area negative 2 pi. Okay, what's the integral from negative 4 to 6? Negative 4 to 6. Answer, so basically the entire thing now, well, okay, I sort of have done this already, right? It's going to be negative 1 minus 2 pi, but then plus this, which is just, that just is has area 4. Yeah. So answer 3 minus 2 pi. And then the last one just makes you jump through, oh no, there are 2 more. A, B, C, D, yeah. E says, what's the integral from negative 4 to 6 of the absolute value of f? Okay, this is kind of interesting. I guess the thing, well, I'll wait for a second to answer that one. Let's do f first. F says, what's the integral from negative 4 to 6 of f plus 2? Okay, this is kind of strange. I suppose you could either redraw this entire function moved up 2, or you could just, I think more efficient, to just apply integral properties and to say that this is the integral from negative 4 to 6 of f plus the integral from negative 4 to 6 of 2, and this is just 10, 20, because this is just a rectangle of length 10 and height 2. And this, we calculated already, was 3 minus 2 pi, so this whole thing becomes 23 minus 2 pi. Actually some work going on here to understand all this. Okay, the last one, probably best to just redraw this picture, and I'm on the last problem, so I'm just going to do it right here. The absolute value of f is this function, which looks just like f when f is positive, but is the opposite of it when x is negative. In other words, just make the whole function positive. And asking for the integral from negative 4 to 6 is now asking for the area under this curve. Okay, and one of the sort of deep principles of calculus, or of integration, is that if I'm continuing to sort of think about this in a meaningful way, if this function f is velocity versus time, then what is the absolute value of velocity? By definition, the absolute value of velocity is speed. That's just what speed is. If we define velocity precisely as the instantaneous rate of change, in other words, the derivative of position, then what about this other word that gets thrown around since 2nd grade, speed? Well, speed is just velocity when velocity is positive, but when velocity is negative, speed is the positive version of that. In other words, we may precisely define speed as the absolute value of velocity. And now this is sort of saying, what is the integral of a speed function? Well, now it just makes complete sense. If I'm going at a certain speed for a certain interval of time, then the area under that speed curve is going to be the sum of all these little rectangles, each of which is the distance traveled on that interval. And because now everything is positive, I can use the word distance. So what is this? It's just the distance traveled. This one was the displacement on the interval -4, 6. It says that when you start here at time -4, you go backwards for a while, then you go backwards a lot, then you go forward some, and you end up 3 minus 2 pi, which is a negative number, from where you started. But now, you're just asking the question, what is the distance traveled on the interval -4, 6? Okay, and I guess I can just answer this now. What is it going to be? This is 1 plus 2 pi plus 4. And so that's 7 plus 2 pi. And so these are two very sort of different questions. What is the distance traveled on the time interval -4 to 6? It's this big positive number. Versus what is the displacement or the change in position. Okay, now for real, the last problem. So this was a homework, was not very time consuming necessarily or algebra heavy, but it did have there was a lot of thinking and understanding, I suppose, built into it. Okay, last one, 49C. What is it? We have some function, and we are told, well, first just 49 just says, we have some function, we have some interval, the interval from 0 to 5 of f, and we're told that this is 4. Okay, and now we just have to do some things. Okay, so part C just says, oh hey, by the way, f is even, and part D says, oh by the way, f is odd. Okay, this is a seemingly bit of minutia, but actually very important geometric understanding, which I don't think I mentioned in any of the videos. It's just in the book. And now the problem asks you to take the integral from -5 to 5 and to figure out what that is. Okay, well the thing is that I just don't know what this function looks like. And you might be tempted to draw this function on the interval from 0 to 5. You might be tempted to be like, okay, I don't know, if all I know is that the area under this curve is 4, then maybe I'll just draw something and just call that area 4. That's not wrong, but it is not, I think it's not open-minded enough of an understanding, because you don't know that this function is positive on this interval. This function might be a mixture of positive and negative. It might be the case that on the interval 0, 5, the function does like, you know, that or something. And maybe this has area like 2, 1, 3 or something like that. So that the integral overall will be 4 if you're following this. But I can't assume from just this information that f is positive, and so I shouldn't draw an arbitrary function which is necessarily positive. But okay, I think it just doesn't, in the end, matter. Because if this function is even, then whatever it's doing on the interval from from 0 to 5, it's just going to do the same thing on the other side. And so we get like a kind of, can I draw this? Sure I can. 2, 1, 3 type situation over here as well. Okay, this is just a very long-winded way of saying that this function on the interval -5, 0 looks exactly like this function on the interval 0, 5 except flipped. And so this is certainly just going to be 8. Whereas here, if this function is odd, what are my odd graphing skills? Well, again, if that's 2 and that's 1 and that's 3, referring to the areas in the traditional sense where we use area to mean positive. Now, if this function is odd, then for a negative x value, it's doing the opposite. In other words, okay, well, you all know what odd means, but it's going to look like that. And so, And therefore, the answer to this is actually more clear if you just do the thing I said not to do, which is just draw it like that. Then what's the integral on the well, the answer to this is just 0. So I'll just leave it at that. The integral of any odd function over a symmetric interval centered at 0 is going to be 0, because all the positive area here is exactly canceled out by all the negative area here, and vice versa. Okay, good. That completes the textbook work, and then there's still a worksheet to go over. Oh man.